All right. Well, hey, welcome everyone to another edition of the Planet Cassandra virtual meetup. Today we have Dmitri Konstantinov, who's going to talk about the Cassandra memory footprint. So this one looks like it's going to be pretty awesome. No pressure there, Dmitri, but those expectations are really high on this one. I'm really interested in seeing what this is all about too. I've done my fair share of Java as well, and it's always interesting to really take that deep look at how memory is being managed. So this one should be pretty cool.
Thank you.
Yeah. Hey, take it away, Dimitri.
Okay, thank you. Let's start then. I have quite a lot of slides. Hopefully, we will have enough time today to cover all of them. Okay, so a bit about me. I'm a Java developer for last 15 years. I'm also designing different kind of systems, different levels, and so on. I work a lot with different open source technologies, of course, Apache Cassandra mostly, but also I have some experience with Apache Zookeeper, Kafka, Hazelcast, and so on. I have been working with Cassandra for almost 10 years as of now, and more than a year and a half ago, I've got Apache Cassandra committer, so I can commit now more and more. And I'm really interested in distributed systems, any topics about high performance, how to squeeze as much as possible from your hardware, and how to make your systems really highly available. So let's talk about memory and about Cassandra. So uh, it's not so rare to see such kind of errors when you are running your Java application and suddenly you've gotten out of memory, or alternatively, you are consuming too much memory from operating system point of view, and Linux ORM killer killed your process. So you are kind of between two enemies. From one side, you cannot provide not enough memory for your Java application because you will get Java out of memory. From another side, if you allocate too much, you can be killed by operating system. So you need to find the middle way. So our goal is to avoid both kind of issues, and at the same time, we would like to get optimal performance for the resources which we have. And to do it, we need to understand how memory is used actually by your application and what kind of trade-offs exist between memory and some other kind of resources, because it's always software about some kind of trade-offs. And to do it, and when you know it, and you also know how to control the real memory usage and how to limit it for your application, and if you know how to monitor, you can do a kind of optimization loop and finally find some optimal state for your application. And this is what we are going to talk about today. And as a bonus, I would like to share some details about how we are solving some different kind of memory related issues in Cassandra and what kind of things I think could be really nice to have in future, because obviously there's a huge room for improvement always. And let's start with the obvious fact that Cassandra is a Java-based application, so we are running Cassandra on top of JVM. And still, I see this kind of frequent uh, simplified use that you are just need to configure your Java heap as much as possible, and Java heap it's only what you need to run your Java application. So people frequently set that limit for your heap size to consume almost all memory, and as a result, you almost always have your application failed. So what first thing which you need to take care of that when you are running JVM, it's not only heap, which in memory we have many different kind of structures. We have off heap, we have memory spent for threads, for internals of JVM like compiled code cache or garbage collection itself. It requires special internal structures to run. It's a huge topic. I'll spend probably another hour to talk just about it. So here I recommend you to check this interesting talk from Andrei Pangin, who is the author of Async Profiler and known JVM engineer. He provides quite a deep view about all these kind of topics. But I want to share just few details, especially about monitoring point of view for your Java application. So you can specify native memory tracking. It's a kind of out-of-the-box option available in your JVM. And for example, let's run basic write workload and warm up our Cassandra to see how the memory is used by it. We are just invoking this command line tool. More details about these tools are available by the links. I will share a lot of links, so for some topics I will just provide some basic explanation, but you can find much more in the links which I will be sharing. And you will get output like this. So it gives you information about memory usage for your Java application. In our case, it's Cassandra. You see that some space is used by classes to keep some metadata and so on. And shortly, like for example, if I'm running Java application Cassandra with 8 gigabyte of heap size, you will see that I was spending quite a lot for other data structures. And if I'm increasing my heap size, I see kind of different distribution. And for example, you may notice for garbage collection, I'm spending about 5% of extra RAM. In my case, it was G1, but it highly depends on what kind of garbage collection you're using. So this line we will discuss a bit later, but so far let's just capture these results and continue. And I would like to follow a kind of request flow in this presentation. So when we are processing request, the initial stage we are receiving data from network, and we have network layer and some sockets in Java, which you think maybe do not consume extra memory except your Java heap object, but it's not so true. Let's do a test. We can open a lot of SQL connections to our Cassandra server, and let's send many batch inserts, which are big, and slow down somehow Cassandra server to emulate that it's probably overloaded. And let's see what is going on with our memory usage. And you may suddenly observe that you can spend quite a lot of memory in such an expected place as your socket buffers. And when you are running a big Cassandra cluster, you have many client applications which are connecting to your Cassandra cluster, having many connections and spending quite a lot of memory to keep that network buffers, it's not so rare. So here I'm sharing few command line comments which you can use to check details about this socket usage. In our case, because I was slowing down processing in Cassandra, obviously we have a lot of requests are sitting in our receiver queue within a socket on operating system level. Can we control it? Yes, of course. Where the list of options, you frequently may notice them in recommended options how to tune Cassandra, but you need to understand that it's a kind of trade-off. You want to have a big buffer to process to have a higher throughput, but you're paying for it actually by allocating extra memory. So just keep in mind that this kind of settings, it's a trade-off. But usually it's okay for you and you shouldn't worry much about it. Just keep in mind when you have too many connections or too many applications that you have some memory consumption here. And if we speak about configuration options, here can we control it? As I mentioned already, there are some parameters on operating system level, but also in Java and Cassandra, we have a set of options which allows us to control this kind of buffer sizes. And because this consumption depends on number of serial connections, and many other resources in Cassandra are also allocated per connection, you may have a case when you want to limit the number of serial connections. And there are such options in Cassandra since version 2. Actually, by default, they are disabled, but it's possible for you to enable limits and to not overload your Cassandra with too many connections opened by an application. And if we speak about monitoring, again, I will highlight every time what kind of configuration options you have and some options and some way how you can monitor it in runtime using different kind of commands or metrics. In our case, we have Gmx metric exposed about number of connected clients. You can also check this information through the node tool, or you can use virtual table and select such kind of information from it. So you can see how many clients actually connected to a cluster, from what kind of version we're using for the driver, and so on, so on. So we have sockets, we can monitor them in that way as I described, and the memory usage, it highly depends on your configuration. And one more aspect which I want to highlight when we speak about network layer, it's about number of concurrent requests. Because if you are sending too many requests into Cassandra and all of them are in process, you easily can consume all memory and just get an out of memory exception because you just eating too much heap to process all that requests. Of course, there is a basic protection against just single big request with a frame limit size. You can limit number of concurrent threads which are used to process native transport requests, but it's not enough because we are doing processing in Cassandra using multiple threads. We are jumping across different kind of queues, and also different requests may consume different amount of memory. So we need something more reliable to limit our memory consumption. And the idea, we need some kind of rate limiter, which we have again for quite a long time. We are tracking how many in-flight request data we have. And the algorithm we can present in the following way. We are measuring actually byte size for the request for simplicity. And we have some basic per connection limit, which is configured by default in 1 megabyte. And we can initially consume from this per connection limit. If it's not crossed, we are just continue to process the request. But if it's crossed, then we are switching to consuming from some kind of quotas. We have a per IP quota and global quota. And we are consuming from them. And if we have some available space, then we continue to process request. But if not, we are in an overload state, and then behavior of Cassandra depends on the flag, which was negotiated between a client and server. And in most cases, Cassandra will just stop consuming from the socket. As a result, we will have a kind of slowdown and back pressure for the TCP socket logic. Or we can just throw an overload exception back to client. And it's client problem now to decide what to do with this kind of overload state. And that settings which I mentioned, the limits, they are configurable. By default, you have that small per connection limit just to reduce contention fighting for global limits. And you have limit per IP and and global limit, which is a proportion for like 10% of your heap size. In this way, we can and we are returning that limits which we have taken during the request processing when we have sent a response back to a client. So we have now gain capacity within our system to process new requests. In this way, we can apply kind of back pressure and to limit number of requests which we are processing. You can monitor it again using Gmx metrics, with a plenty of metrics here. And interesting fact that actually, if you speak about Java Cassandra driver, the last time when I've checked, it supports only the mechanism when we have a TCP slowdown, so it doesn't set the flag to when we expect that Cassandra will send back to us an overload exception. And same story is actually about internet communication, because we have some kind of situation when we are speaking when we have interaction between two Cassandra server nodes. Uh, Same kind of logic, just different settings, and you can also find corresponding metrics within a Cassandra. And at the same time, we may ask for a classical rate limiter, when I just want to say, okay, I just want to handle 10K requests per second, and it's my fixed static limit. This logic is disabled by default, but if by some reason you want it, you can enable it. But I'm not sure if many people actually use it. And additionally to that generic logic which I've described, we also have different kind of protection limits integrated into processing of specific request processing. For example, if you speak about write request, you have maximum size for your mutation and different kind of thresholds for an application to not send a huge batch and do not kill us or to slow down. Same story about reads. In this case, we want to limit our page size or the number of tombstones which we are reading from disk, and we have to serialize and send them across the nodes in Cassandra. All these kind of things are limited again to survive in in some cases. So let's return back to the thing which I highlighted at the beginning of the talk about that strange others category, which is printed by native memory tracking, which consumes quite a lot of memory out of heap. So what is it? If we check that technical talk which I mentioned previously from Andrei, we will know that it's actually allocation through unsafe allocate memory, and it's probably related to direct by buffer usage. So let's analyze it in more details. So we have different sources for the analysis. From one side, we have native memory tracking. We can also check Gmx metric provided by GVM. And finally, we have an option to capture heap dump and find instances of direct by buffer there to see exactly who is using them and how. So let's do it. In my case, for example, I'm capturing Gmx metric. By the way, if you don't know, in Node 2 with embedded Java Swiss knife toolkit or something like Java Swiss knife toolkit, which gives you ability to capture different kind of metrics, and you can also request information from your Gmx beans. In our case, you can see on the screen the way how I can query some GVM metric. So I have one number here. If I'm capturing heap dump and analyzing it using Eclipse Memory Analyzer, I'm getting another value. And so as a result, I have three different kind of values. I have one value provided by Gmx, another value provided by native memory tracking, and third one heap dump, and they are dramatically different. So what is the real consumption by direct by buffers in our system? So let's try to inspect the more detailed source which we have. It's a heap dump. First of all, I see quite huge single direct by buffer in our heap. Let's check what kind of logic is uses it, and you can notice that it's actually GVM itself, and it's really JVM module data is loaded on startup, and it's actually memory map buffer, which we load to speed up loading of Java standard classes. So it's not really a direct by buffer, but memory map buffer when we are loading data from a disk. So we can exclude this, and let's focus on another buffers, which we have quite a lot. And if you check it, you'll see that it's a part of netty library. And Cassandra uses netty a lot to implement all network communications now for the SQL interface as well as cross-node communication. It all works through netty. And netty it implements a memory pool. Why? Because we are working with direct by buffers, which are not fully in Java heap, and it's quite expensive to allocate them and to collect them by GC, so you wouldn't like to do it for every request, you would like to reuse them. So we need a pool, and Netty provides us such kind of pool. And you can check how much memory is used by this kind of pool. And the way how Netty allocates this memory, it's not actually through the standard direct by buffer mechanism, but it uses unsafe allocate memory for performance reasons. So you have to use special way to retrieve this metric. So that's why the metric which we ask GVM for the size of allocated direct by buffers do not display us the real picture. And another interesting fact here that this memory pool it's sharded between threads to reduce contention, and we have multiple arenas. By default, it's like 2 arenas per core, and as a result, memory consumption can be quite big here. Can we reduce it? Yes, there is a plenty of native settings if you want to play with them. I found these two the most interesting. You can, by default, Netty create a number of threads equal to number of cores on your machine. But in reality, when we speak about Cassandra, we are doing a lot of processing in other threads, and just create so many threads is not really needed. Like in my recent performance measurements, I've sent few 100,000 requests per second to Cassandra node, and like 1 or 2 event loop threads, it was enough to process all of them. So you, in majority of cases, I'm not saying in all cases, but in majority of cases, you don't need so many threads, and you can reduce this number, and as a result, you will reduce the memory consumption as well as the cost for operating system to switch your threads and like to schedule them. So it's a kind of one of the tricks which I'm using in my when I'm optimizing Cassandra. Maybe I will submit a ticket for Cassandra to change it by default, but it's probably in some cases for some workloads maybe you need many threads here, but I think we will discuss it. Again, if you want more details about native behavior and how the allocator buffer, the pool is organized, you can check the links on the slide. And another idea here, it's like if you speak about future plans for contribution on Cassandra, currently we are using native 4.1, and we can try to upgrade to newer version of Netty, which contains quite many new optimizations, and plus there is an adaptive allocator there, which tries to be performant and and consume less memory at the same time. So it's worth to try. So we have Netty pool. Actually, majority of that others category, which wasn't unclear previously. It's about netty memory pools. But we are going further, and the next level, when we are processing request, we've received it and decoded from network, and we have coordinator logic. And within the coordinator logic, we have a prepared statement cache, because you wouldn't like to parse your SQL statement every time, consume CPU for it. So you have a cache which contains internal parsed SQL statement information and we store it in a local cache. And key here it's a MD5 hash from your SQL statement text, and the value is parsed entity itself. So it's stored in heap. We are using caffeine cache library to keep this information. You can check more details about the library by the links. And the typical size for prepared statement cache, it's quite small, 32 megabytes. So if you're not doing very tiny Cassandra deployment, you shouldn't worry about it. And average cache size entry, based on my experience, it's about single entry. It's about 10, 20 kilobytes. So you can put like 3,000 statements into your cache. In normal case, it's enough if you are using proper prepared statements with bind variables, then I don't think that you are crossing this limit. Again, if you want to monitor this cache, the activity related to this cache, there are some metrics about it. At least I'm recommended. Probably the second one is most interesting, which you should monitor, and because in normal case you shouldn't evict any statements from this cache or do it rarely. If you see continuous eviction, probably you are writing your queries in the wrong way. And you can check the exact queries from a system table to see the text of the query itself. And we are going through them. And the next topic is the most interesting one. It's probably the most memory consuming. Mem tables. So when we are writing into Cassandra, we have some internal memory buffers where we are accumulating writes to not write every independent one onto disk. We would like to collect them in memory and flash to disk in big batches. So we have many tables. We are writing data into these buffers. And if we are not limiting them, we will obviously get an out of memory exception. So we want to track how much memory is used by these mem tables. From one side, we want to track it per mem table. And we also would like to track the whole consumption. The whole consumption, it's a threshold, it's a trigger for us when we need to do a flashing, and we need to track the memory usage per table because you want to select the biggest table to flash into disk. And the overall life cycle is looking like you are writing into your mem tables, we are tracking memory usage per mem tables, we are tracking overall consumption, and when we are crossing some limit for overall consumption, we are selecting the biggest table and switching our mem table into flashing mode, so it's a read-only. We still read from it, but we cannot write to it anymore. With a new version which we are using for write, and we can flash this read-only table into disk and finally switch to disk version and release memory. As a result, we can use this memory for new mem tables. So we have this kind of life cycle for our mem tables. And the related settings, because the memory usage for mem tables is split between heap and off heap, we will talk about it later in more details. You are configuring how much you would like to use in your heap and off heap for mem table specifically. The default size is 25%, and it's a maximum size. At the same time, you have a cleanup threshold, which defines what percent of this space is a threshold, and if you are crossing it, you have to start flashing. And this threshold, by default, you can configure it explicitly, but by default, it's compute it's calculated using a number of flashes thread. More flash writer threads you have, earlier you start to flash data onto disk. So what happens if we are flashing data slowly from memory to disk? It means that we are still keeping our mem table in memory. We are not releasing it, and eventually you will consume all memory available for your mem tables, and new writes will be blocked and will wait for a free memory. So it's a typical case when you saturate your write capacity for disks, you will see slow down for your new writes, and they will be blocked and will wait for releasing of old mem tables. So it's a kind of back pressure mechanism for Cassandra to not die. So it also means that mem table cleanup threshold, you cannot set up it too high to not get into such situation. And there are two important metrics which helps you to identify such kind of situation. It's when we have too many pending tasks, or when we are trying to allocate memory and the pool is fully consumed and you are blocked on allocation. So if this metric is increasing, you have a problem actually. And one observation which I would like to share here, it's kind of recent one. We've added support for GDK 21 recently, it was less than a half a year ago, in Cassandra 6.0. And it allows us to use generation of ZGC. And interesting fact, at least for the tests which I executed for it, I did some write throughput tests when I inserted a lot of rows into it. The default heap size is not so good in this kind of use case. It's just too big for the settings which I used, and as a result, inserts they start to slow down by garbage collection itself, because the GC, if it cannot keep the concurrent garbage collection, cannot keep the pace, it will start to pause your application threads. And if you reduce memtable heap size, heap space, you suddenly can get like more than twice more throughput in this scenario. Again, it's not a general recommendation because it depends on what kind of workload you have, how much heap do you have. But in the overall idea of this story, it's not always good to have memtable heap space as big as possible. Sometimes small is better. And let's go further. So we've talked about Cassandra lifecycle for memtables, but what's about allocation logic for the data which we have within the tables? So we have inserts into our table, and we have three kind of data which we are sending as a part of insert. We have a partition key, clustering key, and set of value columns. So how do we store them? Because the more optimal way we have to store them, more data we can keep in memory. In memtable, you have less frequent flashing. It means less frequent compaction. You are reducing write amplification factor, and you can use your disk more efficiently if you are compressing data more efficiently into your mem table. So we have such kind of hierarchical structure. We have a partition. Within a partition, you have multiple rows indexed by clustering key, and you have multiple values for your cells. And technically if we speak about internal implementation, which we have right now, in Cassandra, you have a kind of three layers, like map within a map within a map. You have a sorted map on top level, which is per partition. Within partition, you have a sorted map for for your rows indexed by clustering key, and inside on the lowest level you have your cells indexed by column identifier. And yeah, let's skip this part. And technically, if you speak about standard classical implementation, which we had for a long time, you have a concurrent skip list on top level, and we have in memory B tree on middle and low level. And when we speak about how do we store actual data within these maps, we have keys, clustering, and cell objects. And let's skip this part. I think we don't have time today to discuss it, but if you want, we can talk about it later. And as a result, so let's analyze how much Java heap or any kind of other memory we are using to keep these objects. To do it, we will use a Java object layout library. It allows you to see the real memory layout and footprint for your Java classes. And let's, for example, take a partition key, which is a text, I think very typical type. And we have 10 bytes. It's actually ASCII text, so it will be like UTF-8, it will be 10 bytes encoded. And let's print our key structure for it, and you will see that real Java memory, Java heap consumption, it's actually 24 bytes just for this key, because internally you have this kind of quite complicated structure. You have a clustering key object, which has a reference to byte buffer object. Byte buffer object, if you speak about heap buffer, it has a reference to byte array, and finally you have your data in your byte array. So you have quite many objects here, and the total real memory consumption for just keeping 10 bytes, it's actually 128 bytes. As you see, we are paying 10 more times memory just to keep this kind of string. And same kind of story for clustering key, same kind of multiple objects we have to keep to process our clustering keys, and a bit simpler but similar story for cells. Again, you have 3 objects to just keep 10 bytes of your information. So we have many overheads here. What can we do? So obvious idea, okay, we have byte buffer. Let's move values to a heap and use direct by buffer. Doesn't require a lot of changes, and we are eliminating this byte buffer. This data are not anymore in our heap. It's not so ideal because direct byte buffer itself it's quite heavy. It's actually bigger than heap byte buffer, but still we have significant improvement, reduction in our heap size. And actually, I'm speaking about memtable allocation type. So the previous value, default one, it's a heap buffers when you have everything in your Java heap. And the option which I've just described about direct by buffers, it's of heap buffers. So when you switch into this option, you are doing this exact kind of change in your memory for memtables. But can we do better? Yes, you can get rid of byte buffer objects at all. Actually, the idea is you can allocate memory in native region and just store a pointer to it as a one and use this memory, work with this native memory in some way. Now it's unsafe, but probably later we will do something better using new Java API. And you are just keeping that data encoded into your memory. And it looks like this. You have a single Java object, native cell, which is quite tiny because you just have 2 fields, column metadata and long pointer to native memory region, and all other data about your value, like timestamps and so on, and value itself, were stored in native memory. And as a result, your heap consumption is much better, and you can save a lot of Java heap by switching to this mode. And from configuration point of view, in your Cassandra YAML file, it actually it's called heap objects. So when you are switching to this mode, you are using that logic which I just described. So kind of small summary. We have memory allocation type configuration in your Cassandra YAML file, where you can select allocation type. If you worry about optimizing your Java, about optimizing your memory usage, the most optimal parameter from this point of view, it's the most optimal option is of heap objects. And there are two generic limits: how much time you want to spend for your heap and of heap space. For mem tables, we're configuring the values on the screen, and by default, it's a quarter of your heap size both. Can we do better? Actually, we can try to reduce object overhead because so far I've talked about the logic which I've already implemented in Cassandra, but now I'm talking about possible future improvements. So each Java object has a quite big header. It depends on JVM, your JVM type, your heap size, and so on. But let's, for simplicity, say it's 12 bytes. It's so as a result, your total size, as you see, quite big, and half of it for small objects like native cell are consumed by this header. But there is optimization in JVM itself, which has been finally released in Java 24, and I think in Java 27 it's a default even now, which reduces object heap size, object header size, and adjusts in 8 bytes now, and potentially in future maybe it can be even smaller. So as a result, you can reduce your Java objects overhead quite a lot. But the question is, for native cells, do we get a benefit immediately? So let's try to estimate the results using the same tool. We can just create a heap dump and ask this tool to clarify for us how much memory we are using now and how much memory we will use if we have that new optimization. And the idea is, speaking shortly, that you will not get a lot of improvement for Cassandra by default. Why? Because we have memory alignment in Cassandra. So objects by default were aligned by 8 bytes. So currently we have 24 bytes, which is an ideal size for Java object because it's already memory aligned. And if you are reducing your header for 4 bytes, you will have 20 bytes, but you will spend some space just because of alignment. So unfortunately, compact objects by default, they will not give a lot of improvements for native cells. It doesn't mean that it will not give us improvement for other objects in Cassandra. It definitely will be better. But for native cells, we will have to do some extra work to reduce size. For example, we can take call metadata and replace this reference with some shorter number to make the object smaller and finally get something like 16 bytes. But can we do something else? Actually, yes, and we already have this solution available for you right now, even in Cassandra 5.0. You can skip some memory usage by the collections which I mentioned. You have many kind of maps, and on top level we have a skip list map. And we can move this almost whole structure to a heap and use a try as a data structure, which is fully of heap. It duplicates prefixes, so you can save extra memory even in your of heap region. It's more tricky from concurrency point of view, but for real scenarios it's okay. So the result, we can replace this top level with an of heap structure and save memory here. And it's, as I mentioned, it's already available. You can enable it and use it. And I would say, as of now, it's probably the best option which you can do in Cassandra 5.0. It's to enable trimem tables. And if we speak about future, I think sooner or less we will have to get rid of that cell objects. They are just too expensive. There are several ideas how to do it by replacing it with a more advanced trie structure or maybe by using byte addressable format. It's a one way, and I think it will be the next major step in improving Cassandra performance if we do it. And the second idea, we can make more compact encoding of data for our native cells, just because currently the structure is simple but not the most compact one. And the third idea, we can finally have that support for GDK25, get that compact headers, and get access to some other technology, some other new APIs which we have. And hopefully in near future, GTK will get finally support for Java objects, for value objects. And we will be able to use memory more efficiently in Java. So it's about memtable. I will skip this part, but you can check the slides. I can give you it here. I have some detailed calculation how much memory we are using if you know your schema. So you can check it in offline if you want. And let's go to the way of working with disk. While we are working with disk, we still have to use some memory. And the first layer, when we are reading from SS tables, we really do not want to read from all of them. So we need to know which one which one have really our data in. And here we can use a probabilistic data structure, Bloom filter, which gives us answer maybe a particular SS table have data, or definitely there is no data in this file and you don't need to read it at all. And in case of Cassandra, we are using partition key to decide. So it's kind of per partition level, not per row level. And internally, it's a kind of, for me, I think, if you speak about idea, it looks like a hash table without resolving collisions. You have a key, you are calculating hash function for your key, and hash function points you to a position within an array, but array, it's just a bit array with when you are setting 1 if you're inserting into this structure, and 0 means you haven't inserted into it. And when you are doing a check, it's the same logic. You are calculating hash, you are checking the array value, and if we have 1, it maybe means yes, or you have got a collision. Or if you see no 0, it means no, definitely there was no value inserted for this position, for this key into this structure. And to reduce probability of the error, you can use multiple functions here. And Bloom filters, where as you got, we have them per SS table. They are mutable. They stored on disk. So when you are flashing memtable to disk, you are creating a Bloom filter, and they are loaded to memory. And we keep them fully in a heap. So there's no overhead for Java heap, but you consume some memory, native memory to keep these kind of things. And size of Bloom filters, it depends on how many partition keys you have. Again, I would like to highlight that it's a per partition, not per row. And interesting thing that you maybe you can notice already, because we are using hash function, the size of Bloom filters doesn't depend on the length of partition keys. So even if your partition key is huge, still the size of Bloom filter is constant, and it depends mostly on your configured error probability. So you are defining what is the chance for false positive, and you can configure it per table. By default, Cassandra uses two values. If it's a leveled compaction strategy, then it's a 10%. And for other compaction strategies, it's a 1%. I'm not sure about unified compaction strategy. It's probably what I need to check in offline. And how can we monitor this kind of consumption? You can check node tool table stats, and you will see Bloom filter of heap memory usage output, or you can check again some GMX metrics and some kind of calculation. For example, let's assume you have 1 billion keys, partition keys, and for false positive chance 10%, you will consume 600 megabytes of memory. If you are reducing chance of an error in 10 times, you will pay twice more memory. So it's again a trade-off. You are reducing the probability to read disk in 10 times, but you are paying twice more memory. So you can select what you would choose. And here I have a link to the calculator, which helps you to check how much memory you need. Or you can check Java code for in Cassandra itself and use it to do same kind of calculations. So we have Bloom filters which live completely in a heap. But then we are switching to reading from SS tables. And when you are reading data from SS tables, SS table, it's a set of, it's a sorted set of partition data. So when you are reading data, you need to find the exact position within your data file, how to read data from that position. And to do it, you have an additional index file, which contains partition key and index for information which points to that position. And to find index file, it's quite big as well. We cannot put it into memory. And you have to do binary search within this big file, which is not so fast. So the idea is let's do a sampling from that index file and create an index summary, which is a sampled index file, which we can keep in memory. And it's a gain of heap memory. So we are not consuming Java heap to keep in this data. So we can scan this index summary and to find the exact, to find the range of keys, the range of positions in our index file, and finally do a search and find the exact position for our key.
Dimitri,
So
just a reminder, we're coming up on time, so about
yeah,
4 minutes left, okay?
I think I have probably 5 or 10 minutes left. Yeah, so
All right.
it should be fine. So we have as a stable index summary stored in a heap. And when we have lack of memory, because the amount is limited, we can reduce the sampling interval for SS tables, which we are not using frequently, to save some space. Again, there are some settings about it on table level as well as generic one. And monitoring options. Same story, fully of heap. And another thing, we would like, in some cases, we would like to skip that reading of that index file at all, especially for hot reads. And we have a special cache for it, which is called key cache. When you are storing position, you're storing your partition key and corresponding offset within your file. And it gives you faster read, but it stores in heap because it's kind of mutated structure. It's again based on that caffeine library, which is quite smart in caching. And you have configuration which allows you to control it, again per table and generic one. And same story about monitoring. You can check this information in Node tool with the key cache property there and a set of Gmix metrics. And let's add it into our summary. And important thing, additionally to try mem tables, there are also try SS tables. They're also available in Cassandra 4.0, and they use a different way to store indexes. And there is no need for index summary there, and there is no need for key cache there. The idea is that try index is compact enough, then, and you have upper levels of that tree-like structure naturally cached by operating system page cache. So we can rely on it. As a result, there is no usage by this type of SS tables or this of memory for this kind of structures. The next thing, probably one before the end, it's about compressed metadata. We are compressing our SS tables. We are compressing them in using chunks. And when you are reading data by offset, you need to find the exact chunk position to read data from. And when it's uncompressed, it's easy because all chunks have the same size. But once you compress it, all chunks are different and you cannot find easily the offset. So what we can do here, we have to create a mapping. It's called compression info. When you have a chunk, and for corresponding chunk, you have an index you have an offset position for compressed chunk in the result file. So we can do a translation. And this compression metadata, again, we are storing in a heap. And it's persisted as a part of SS table information. It's quite compact. You are spending just 8 bytes per chunk. And it depends on chunk size. More smaller chunks you have, more offset you have to store. So if you have chunk like 16 kilobyte, this kind of amount of memory you are spending. If you are decreasing your chunk length, you are spending more memory. So again, it's a trade-off. You may reduce your chunk length to read less data from disk, but you will pay for it by increasing your compression info size. Again, it's configurable. You can monitor it using Node tool and Gmix metrics. And let's switch to the last but not least. We are speaking about operating system page cache. So Cassandra naturally relies on operating system to cache files when you are reading data from your SS table files. The SS table files can be cached by operating system. And Cassandra tries to optimize the way to work with that cache and keep as much as possible in the page cache, but of course it's kind of if you don't have a big enough page cache, you will consume more. You will read from disk from time to time. And you can monitor it. There are different kind of commands. There are special tools as a part of Berkeley filters. And there's a PC stat tool which shows you exact percentage of caching per file. So if you want to tune it on that level, you can use this kind of tools. And the size of page cache depends on your configuration, but I would say typically like if you have 24 gigabyte of RAM, you will probably give a half to page cache and operating system, and you should give not more than 31 gigabyte of RAM for your heap size and spend all others for between a heap and page cache. And let's summarize what we know. Cassandra memory, it's not just Java heap, it's much, much more. Your memory footprint footprint depends on configuration, your schema, how many columns you have, how many tables you have, and so on. Amount of data which you are storing on disk, number of your SS table files, configuration for your chunks, and so on. On your network activity, even, or like we discussed about sockets. And also, you should, if you are still using an old version, you should try a new one, and you should try new features like try mem tables to optimize your memory usage. And when I was preparing this kind of slides, I've noticed that not so much information in the internet about this topic, but there is one new interesting source from Axinops guys. They've done really nice job, and there is a good description of memory footprint actually given by them. So I'm sharing a link here which you can check for additional details of the topics which I discussed. I think that's all from my side for today. Hopefully we're able to get it. It's not the whole story. Actually, I've skipped some kind of topics where a lot more structures and so on. But as you see, we already spent we spent full hour just discussing these items. So it's probably time to stop. And if you have some questions, I'm ready to answer.
Thank you, Dimitri. I do see a question in the chat. Where Raj Sekar, if I'm saying that correctly, I apologize. Or incorrectly. Where does file cache size in megabytes reside? Then he says, I mean the chunk cache. Is that something that's in the
Uh,
YAML or is that located in another spot?
so I think file cache size in megabytes, it's a configuration in Cassandra YAML. It's about chunk cache, which I haven't covered, but I have actually extra slides about it, I think, in somewhere here. Yeah. So the idea is, if you speak about chunk cache, like we are reading data from SS table, it's compressed. We are spending resources CPU to decompress it. And for hot data, we would like to spend these efforts. And next time when we are reading it, just to read something from memory in uncompressed way. So here we are using again the same caffeine library, and the index in that library, it's a heap. So you are spending some heap to to keep the metadata, but the chunk itself, it's enough heap. So we have a kind of mixed structure, partially sitting on heap, partially sitting on a heap. But interesting fact about chunk cache, it's yeah. So it's again trade-off, disk usage versus or disk and CPU because of compression and memory. I have some numbers about overheads and so on, but people observe that chunk cache frequently makes latency worse, and it was disabled by default in 4.0. So if you are using any supported version of Cassandra now, you by default have the chunk cache disabled and you do not use it. That's why I haven't mentioned it, but maybe in some cases it's helpful. So if you speak about configuration options, you see them on a screen. You can control them, and there's some ways to monitor it. But test it before trying to enable, because again, people frequently report that it doesn't worth it, and operating system page cache is better.
So not
Yep.
really a question, but just a comment. I really liked how you went over the like some of the memory bloat that can go with, like partition keys and clustering keys. And I like your example of like showing, hey, this is 10 bytes, and then
Mhm.
after everything gets applied, it turns into what was it, like 128 bytes or
Yeah, like
something like
10th
that.
time overhead, yeah.
Yeah. That's pretty crazy. I had no idea that there was all that kind of extra headers and whatnot that gets added onto it before it gets stored.
Yeah, the positive side as a result, it means that we can get a probably dramatic improvement in performance if we can do it better. So we have plenty of space to improve Cassandra performance. It's definitely like not end of story. Even if Cassandra exists for a long time, we can do it much better. And it's a
Yep.
positive side.
Um, anyone else? I know we're over time here, but as long as Dimitri can stay on, I suppose
Yeah,
we could
I
answer
can
some
be here
questions.
for half an hour at least.
Yeah, I saw that Raj Sakar, followed up, but then he gave you a bunch of thumbs up. So I don't know if you answered both all of his questions or not, but it looked like you maybe did.
No, I got another question actually. Hey, hi Aaron,
Yeah.
hi Dimitri. This is Raj
Hello.
over
I
here.
am.
So the question is basically, see, you mentioned right, say my direct memory, which we assigned, we normally configure in the JVM server options, right?
Yeah, we
Direct.
have a limit for direct memory, but again, it's applicable only for direct by buffers. So the things which we allocate through unsafe or yeah, like that all that of heap structures like compressed metadata, Bloom filters, and so or of heap mem tables, were all going behind that limit actually. So that limit have. And it's mostly about probably about file reading because when we are reading data in Cassandra, we are using Java Neo API and oh, actually Java file API it relies a lot on native on direct by buffers. So it's mostly applicable for that part if I'm not missing something. So just be careful that if you have that limit, set, it doesn't mean that Java, the the whole memory region used by Cassandra outside of heap will be limited by this value. Definitely not.
Right. Just so
Yeah,
basically,
but
you
yeah,
clearly mentioned in your call in your discussion that these SS table components like Bloom filter,
yeah,
compression metadata, index summary, these all reside in native memory.
yeah. We allocated through the unsafe API now, and it
Uh,
goes directly to native allocator, which is connected to your process. Like
so if we understand it
yeah,
this way, that heap memory is a big chunk, which is basically, let's say we assign it at 24 GB, all 24 GB is being consumed. So basically, the memory usage, the actual memory on a system, let's say it's 125, 128 GB, 128 GB total memory. Out of it, let's say we assign heap memory as 24. 24 gets allocated right away. It's not touched. It's exclusive for heap memory, right? For Java objects. Now, rest basically, can we divide that into two major chunks like this direct memory and a native memory part? I'm talking about off memory.
yeah,
Can we divide
it's what I've tried to do here. While it's quite complicated, it's actually in this table I tried to do it. Like you see, I tried to calculate it for a typical, like if I have a 8 gigabyte of, because many of these parameters were calculated by Cassandra as a proportion of your heap size. So let's assume
right,
we have a 8 gigabyte of heap size, then you have a quota for mem tables, for example, and so like quota for mem tables enough heap if you are using enough heap, and so on.
right,
So it's what I try to do here as a calculation, but it's quite tricky because like many structures are dynamic and you cannot really limit them. Like for example, for Bloom filters, it's just proportional to your amount of data. There is no physical
right,
limit. You cannot say that Bloom filter size is limited by this value and we cannot use it more. It's just dynamic. It's the same story about compression metadata. For caching like
right.
things, you can limit it. Like index summary, for example, or that pulls within Netty, you can control them explicitly. So I
Right.
would say like like if you speak about some baseline and it's actually implemented in Cassandra shell scripts, you are configuring your heap size between, I would say, a quarter of your RAM to one half in that range. And the remaining memory you are using for of heap structures plus page cache in operating
Right.
system. And one more thing which I haven't mentioned, but I think it's an important one. It's about configuring heap size. If you speak about if you speak about garbage collections like G1, CMS, and so on, there is a such thing in Java as compressed references. So when your heap size is less than strictly less than 32 gigabytes, Java can use a more optimal way to store references in Java objects, and instead of 8 bytes, it uses 4 bytes. Once you
4 bytes.
cross that limit, you are getting that references long, and suddenly your heap usage is like it's much less not so optimal. So that's why frequently there's a recommendation do not cross 31 gigabyte
Yeah, right.
for your heap.
Right.
And second important fact, especially taking into account Java 21, which is coming for Cassandra and so on, ZGC doesn't support compressed references. So if you enable ZGC, yes, you are getting better pauses, less pauses, better latency, but you are paying for it with expansion of your heap, because even if you are configuring small heap, compressed references do not work for this garbage collection of algorithm, unfortunately.
Right.
Sorry, yeah,
Right. Right.
maybe I'm just sharing too much extra comments, but just kind
Uh,
of things
right.
which I
No, no,
think
no.
are important.
The fact is, we do not get such details across if we also
Yeah.
scan through documents, right? And that is so
Yeah, it's
basically,
why I decided to share the talk, because that Axinops doc, which I shared at the end, it was probably only the good resource which I have found so far. All things which I've described so far, it's based on my experience or based on the source code analysis. So like, because I'm spending
right.
quite a lot of time in Cassandra internals, I just have taken all this kind of information from source code, but obviously it's a
Right.
kind of very time-consuming way to do it. So
Correct. And Aaron and Dimitri, just to let you know, we have at least 6 members from our team who basically we work together in a team. We're here on this call just for the session because we quite often see these memory issues, right? And we've been trying a couple of months to dig into deep dive into what exactly is the memory footprint in Cassandra. How do we understand it? For example, quite often we keep on getting this out of memory exception for direct buffers, right? Uh,
interesting. Maybe you can share it in our Slack. I can try to take a look at least to identify what kind of what kind of out of memory, because there are different kinds, and maybe I can advise you to look at that direction. If you still do not know answer, if you know answer, still makes sense to share just for other people to know what kind of issue they may get.
we what we figured out is basically in the direct memory, chunk cache takes a lot of space. Let's say the direct
Mm-hmm.
memory is being assigned a hard limit of 50 GB, and our chunk cache is, let's say, 40 GB, right? So
Mm-hmm.
we try to understand is, our observation has been this way, that out that 50 GB is the bucket of direct memory, out of which 40 GB is being consumed by, let's say, chunk cache. So we have basically 10 GB left. For what? 10 GB left, maybe, which you covered, right? Netty pools,
Mm-hmm.
sockets. That's what I think. We try to look
Okay,
into open
yeah.
source code as well. Yeah, yeah.
If you can capture heap dump for that process, I understand that it will be huge, but if you have an ability to capture it, you can do the same kind of analysis which I've done at the beginning of this session when was talking about direct by buffer. You can just find all direct by buffers which are stored in your Java heap, and to
Right.
check what kind of data structure are keeping reference to it. So as a result, you can classify how exactly it's used. It's one thing. And another thing, I was thinking a lot, and probably I'll finally create a ticket for it in Cassandra. Uh, I think it would be very helpful to have an additional not to command, which gives you kind of memory layout details, and it will summarize in single output all these kind of numbers which I'm sharing here. If it will
Right.
put it just like in a single portion, and you don't need to collect it all across hundreds of metrics, it would be really helpful. So it's probably what I'm going to create soon.
Right.
Yeah, Raj, if you have like follow-up questions too, I'd encourage you to go ahead and open up the the Apache Slack and look for the
Yeah,
Cassandra channel, I mean, we're
Yeah.
all in there. We're all happy to,
yeah,
answer and help out too. And then to Dimitri's point as well, then a lot of folks will be able to see those questions and the
yeah.
answers to them if they have those
Right.
same problems. So that's what I'd encourage you to follow as well
Sure.
too.
Yeah, plus you can share like exact if you at least share exact stack trace details, it would be already helpful to
Right.
answer more precisely on your
Right.
question. Yeah,
But yeah, that's a good idea. Definitely, I'll try to have this heap dump taken, and maybe
yeah,
that would fairly good
yeah.
approach.
It will show you where exactly what kind of logic exactly allocated direct by buffers, because the memory spent by buffer it's out of heap, but you can trace through direct by buffer objects who is doing it.
Right. Right.
Okay.
So right. So no, nothing. Go ahead. Go ahead, Dimitri, please.
Okay, regarding the book, I don't think it's a big enough for a book, but I actually even created a ticket, but haven't had time yet to write down about it. So I had a ticket about documenting these kind of things in Cassandra documentation about memory usage in more details. And again, as I mentioned, Axinops guys they did a good job, and actually they wrote same kind of things which I just wanted to write. That's why I'm sharing, highlighting it again and again, because it's really helpful source of information. They do not pay me for this advertisement, but thanks for them to share it in public. Yeah, I'm
Yeah.
speaking about this link. Check it. It's really helpful. So it covers almost same topics which I was talking about.
Dimitri, it
It's
looks
just
like Yuki has a question. I see the hand
yeah.
raised.
Yeah, yeah, thank you. Thank you so much, Dimitri, for sharing all these things. Just a quick question. So, basically, we are also trying to see how we decide the heap sizes for Cassandra,
Mhm.
especially after we moved from maybe G1 GC to Gen Z GC, like we no longer has compressed ops, that sort of
Yeah.
thing. The other thing is that Gen GC is like having lots of like much lower pauses, which means we
Mhm.
might be able to tolerate more like GC cycles or more GC pauses. What's your personal like thought on like
Yes.
how
So I think if you use ZGC, especially generational one,
Mhm.
uh, and you have enough, and you physically have a RAM, you can allocate more for Java heap, because like as you see, wait, let me find it. I mentioned it when I was talking about Java 21, that in my tests, because I have limited amount of RAM in my lab, I have to reduce mem table space to make the GC happy. And it because I had like 31 gigabyte of RAM, which it's configured by default because I'm switching between garbage collectors, but for, as you mentioned, for ZGC, compressed stops are disabled, so there is no much worry to cross that limit. And I think you definitely can try more, and as a result still like and keep mem table heap size larger. So I would try like I would try it 42 or even more gigabytes of RAM if you have it available. But again, just leave as much as possible for page cache because it will make your reads more efficient from disk. So it's
Yeah. I mean, yeah, we definitely like we want to find, the balance point, like how large the heap should be, because
yeah, and it's highly depends also, unfortunately, on workload. Like for example, if it's read mostly workload, there is no much benefit in keeping a huge mem table and reserve memory for mem tables. In this case, it's better to give more to page cache and to read less from disk actually. If you are right, if your workload is more focused like write dominant, then it makes sense to try to allocate more Java heap and allocate more mem table space to allocate them to just collect more data in your memory in mem table as a buffer. Probably if you have updated rows, they will collapse within a mem table and will not go to disk, and flush less frequently to reduce compaction overhead. So I would say there is also dependency on what kind of workload pattern do you have. If it's a read more, give more to page cache. If you write more, probably it makes sense to extend your heap size.
yeah, I think that makes sense. Like it's very workload dependent as well. Yeah.
Yeah.
Thank you.
But I would definitely try, like if you have capacity, try more. But again, I think it's only for the tests can be decided, unfortunately.
I see.
All right. Well, with no other questions, I suppose we could close it up. Dmitry, thank you so much. This was awesome. I'd just like to echo what I'm seeing come through in the comments of just like how much is here and just how deep you went and just it was really great to kind of hear this all out in one place. And hey, thank you for coming out and speaking. We really do appreciate it for sure.
Yeah, thank you for having me.
Of course. All right. Well, hey, thanks a lot, folks. Mariah, do you have anything to add?
No, but just to reiterate, if anyone has a topic that they would like to present later on the year, please feel free to reach out to myself, Aaron, Rahul on the Cassandra the Cassandra Slack, and we'd be happy to have you.
Yeah, probably one question from my side. What is our process to share slides? Because I have a lot of references and probably guys want to
I,
click it
I don't know
after.
that we do a whole lot of slide sharing, but I can tell you that this video will end up on the Planet Cassandra YouTube channel for sure. If you
Okay,
wanted us to
yeah.
share the slides, you could put them in a Git repo and we could go ahead and link them in like the description. That
Yeah,
might be the
I think
best
it's
way
a
to
good
go.
I think it's a good idea. So let me publish it in a Git repo and I will share a link with you.
Yeah. Yeah, that sounds great.
Okay, good.
All right. Hey, thanks everyone. We'll see you all next time.
Thank you. Bye bye.